morning, fellow lecturers and deputy director. My name is
Yeah.
I use the mic.
Use the mic.
Oh, okay. Okay, can, okay. So sorry. Okay. Oh, close. Okay. Okay, good morning, fellow lecturers and deputy director. My name is Sing, and here with me today is Jonathan. So today we will be presenting our final year project, the Industrial IoT Fuel Cell System. Okay, so before I start, I would like to thank our supporting lecturers, Dr. C, Dr. Yip, Dr. Chu, and Dr. In their immense support of the developing of this project. So now I'll be moving on to the table of content. So to begin, I'll be talking about the project objective, hardware systems, software systems, data analysis, and be ending off with conclusion. Okay, so before I start, here are some of the terminologies that we will be using in today's presentation. Have a quick look before I move on to the project objective. Okay, so the project objective. Okay, the purpose of this, okay, so before I start on the project objective, we need to understand that our project is a standalone project, which means that it does not require any external power and is a self-powered system. So the main purpose of this project is to remotely monitor the working conditions of the MFC, also known as the modular fuel cell, and to log real-time data for analysis purposes, and last but not least, to predict the duration of fuel consumption. So now, you have seen this project in the previous semester. So what has been changed? What has been significantly enhanced since the previous project? So first off, we were able to establish a connection between the modular fuel cell and the MyReal microcontroller. So from there, we were able to extract the various parameters from the modular fuel cell and upload it to our cloud-based visualization platform, SystemLink Cloud. Next, we want to log the data for data analysis purposes. And how we do that is that we have a remote data logging. Next, we have a remote data logging machine where we log the data from our cloud-based visualization platform, SystemLink Cloud, and after which we will analyze the data using that machine. Last but not least, we have web page designing. So the app and the software that we use for web page designing is called GWeb Development Software, which is another product of NI. So now, I'll be passing my time to Jonathan, where he will be talking about the hardware systems. Jonathan, please.
Okay, so thank you, Ting. So for this hardware systems we have used is the MyReal and the 4G LTE router, and also the the data logging PC. This is our overview of a system architecture here. So this is like the MyReal, got the DWM313, and also the data logging device. So this is our scalability of our project. So the grayed out areas are the ones that we are trying to further enhance, and also for the clients to see the other parameters that it is visible on SystemLink Cloud. And here are some of the internal components of the MFC. So we have the reformer, the fuel cell stack, the hydrogen pump, and the hydrogen storage. So let us focus on the reformer and the fuel cell stack. So here's a rough idea of how the fuel cell works. So the hydrogen gas will enter through the anode anode side, and will have a chemical reaction on the anode catalyst, which is basically made out of platinum nanoparticles. So there will be a chemical reaction, and then it will have a high positively charged hydrogen ions, also known as protons, and then they will be going through the proton exchange membrane, also known as the PEM. So there's this electrons will exit through a wire to the load, which is generating power. So in the end process, there will be protons and electrons will meet again, and will have the formation of the hydrogen gas, which will be combined with the incoming oxygen, which will be produced as water and also as heat as our byproducts. And there will be unused hydrogen gas as well in this process. So let us move forward to the reformer.
Okay, thank you, Jonathan, for explaining the working conditions of the fuel. Thank you, Jonathan, for explaining the working conditions of the fuel cell. So now let's take a look at what happens to the unused hydrogen from the fuel cell. So unused hydrogen from the fuel cell will flow to the catalyst to react with oxygen coming in from the air inlet. This will result in an exothermic reaction heating up the catalyst and the catalyst bed. Next, a mixture of water and methanol will flow into the vaporizer and be vaporized by the fuel cell's byproduct heat. Now, the methanol and water mixture will be in gaseous state and flow into the catalyst bed, producing carbon dioxide and hydrogen. So as Jonathan was mentioning just now, the fuel cell only requires pure hydrogen. So that's why we have a purifier there, which will purify out the carbon dioxide to only produce pure hydrogen as this output, or as its byproduct. So in this steam reforming method, we will collect a total of 3 different parameters. First, we have the purifier temperature. Next, we have the catalyst temperature. And last but not least, we have the burner temperature. So now we will take a look at the software systems. So here are some of the software that we have used in this project. First, we have AutoCAD Electrical, where we draw our single line diagrams and schematic diagrams for the wiring of our cabinet. Next, we have LabVIEW 2019, one of the programming environment where we use to design our programs. Next, we have GWeb development software, where we use to design our web page interface. And last but not least, we have SystemLink. So now I'll proceed on to the codes, also known as the block diagrams in this project. So this first code that you are looking at is the sending data to cloud using the MyRio microcontroller. So this code is actually embedded into the microcontroller, and after which mounted onto the cabinet, and it will extract data from there to send it to SystemLink Cloud, our cloud-based visualization platform. Next, we have logging of data from the SystemLink Cloud. So how do we go about doing that? We have this code which will be hosted on the remote data logging machine, which will log data from our cloud-based visualization platform, SystemLink Cloud, before we take the various parameters and analyze them. So last but not least, we have the web page block diagram using GWeb development software. So right now, what you're looking at is only the block diagram. So later I'll pass my time to Jonathan, where he'll talk more about the front panel of this GWeb development user interface. Jonathan, please.
Thank you, Ensing. As you can see here on this web page that we have designed, Ensing is passing around the QR code to scan the QR code so you can see the front pages for yourselves. And by doing that, here are some SystemLink Cloud features that we have discovered. So we have the data, security, and visualization. So data is, what it does is to host the parameters, and the security is to create the API key, also known as the application programming interface, which to allow the established communication between the MyRio and the SystemLink Cloud. And the visualizations is the one that we host the web VI onto the web browser that you have just scanned the QR code on. And here is our data analysis. So here's the problem statement. How do we predict duration of the fuel consumption? So there's one method that we have used is the trapezoidal rule using integration. So by using this rule, so we can find the energy under the graph to determine the methanol mixture that we have just consumed. So this is the data analyzing and calculation using LabVIEW. Here's the block diagram. Here's the graph that the LabVIEW has plotted out for me. And here is the formula that the LabVIEW has provided also. So further on, like what is this trapezoidal rule all about? So this one is consists. So it breaks. So it's like So it's like evaluates under the area under the graph by dividing it into total area of smaller trapezoids. That is like, as you can see, this little tiny strips. So the more number of strips, the more accurate of the area will be. And further on, I have used simple calculations provided by Dr. Yip here. So it's like, so you can find the estimate number of days that the methanol mixture that can consume. So after all these calculations, the estimate number of days for the MFC to consume a 20-liter carboy is approximately 15 days. So I'll move on to the conclusion.
Thank you, Jonathan, for taking us through the web page interface and the data analysis part. So in summary, some of the things that we went through today would be the system architecture, the scalability of our project, the steam reforming method, and the fuel cell. So as Jonathan was mentioning in slide 10 just now, he mentioned something called the fuel cell stack. So what is a fuel cell stack? A fuel cell stack comprises of 2 or more fuel cells put together. So on average, a fuel cell will produce about 0.6 volts to 0.8 volts. So if let's say you want to power up maybe a DC device that is 8 volts, so you will need 10 fuel cells put together, and that is when you call it a fuel cell stack. So the fuel cell stack has a scalability in which you can increase the number of fuel cells to produce a higher output voltage, or you can have lesser fuel cells put together to produce lesser amount of output voltage. So in conclusion, here are some things that we have learned in this final year project. So first off, we understood the working conditions of the MFC and its internal structure. Next, we learned new software skills such as web page designing using GWeb development software, and also a cloud-based visualization platform, SystemLink Cloud. Next, we also had data cleaning and data analysis for our prediction. So data cleaning, we use Excel, and data analysis, we use trapezoidal rule in LabVIEW by Jonathan. So last but not least, we hope that by building this project, we can build a more sustainable future for Singapore. So thank you everyone for your kind attention. We hope to invite all the guests to look at our physical product. Thank you.